Hello and welcome to the latest webinar by BYK-Gardner. My name is John Clausen. I'm part of the marketing team here at BYK and I'd like to welcome you. Today's presentation is part of our office hours format. If you're unfamiliar with office hours, we run these monthly and it's usually a short presentation, usually 20, 25 minutes, and then it's up to you to drive the discussion. If you have questions, if you have comments, if you have challenges in your own facilities, please log them in the chat box because about half of this time here today will be discussion. We are also recording this, and immediately following the presentation, you'll receive an automated marketing email with the link. You can listen, watch later, share it with colleagues, whatever you like. Happy Valentine's Day. I do not suggest using the recording for a Valentine's Day celebration, though. I've heard that's happened in the past and it's gone badly, so do not do that. So our presenter today is Mr. Andy Stummer. He is our Director of Dispersion and our VMA-Getzmann for the US and Canada, and all knowledge, all knowing dispersion and media milling. And one note too, in talking with Andy yesterday or the day before, we decided to split this office hours into two parts, just because there's so much material to cover and we want to include that valuable discussion time. So this is part one. We did schedule part two coming up in a couple weeks. In the chat, you'll see the link to register. You'll also get the invite, but it's scheduled for Tuesday, February 27th, same time. Alternately, if you can't attend live, register anyway, because we'll make sure you get that link of the recording. So with that, let me turn things over to Mr. Stummer. Andy, welcome.
Hey, John, thank you, and welcome, everybody. Happy Valentine's Day. As John said, please don't use the recording for the Valentine's Day. So, as John said, we decided to actually split the dispersion review into two parts. Dispersion is actually two parts. So we always have the first part, which is we call that pre-dispersion, and the second part is actually what we call fine milling or grinding, which would also be part of dispersion. But because this is office hours and we're limited for time, we decided to actually do this in two parts. So today is part one, where we actually talk about pre-dispersion and what's important when using a dissolver and the different types of dissolvers. And want to start and lead into just giving you guys a little bit of an introduction about VMA-Getzmann, who they are, and the relationship with BYK. So basically, VMA-Getzmann, as you probably are familiar with, is a high-end Dispermat manufacturer. They own the trademark Dispermat, the logo, and they are a German company. The Dispermats are manufactured about 30 miles east of Cologne, which is kind of in the center of Germany. VMA-Getzmann was founded in 1972 by Hermann Getzmann, and the company is now run by his two sons, Christian and Martin Getzmann. It's still family owned. They are global. They have over 70 employees just working out of Germany, and then over 100 globally. About 6 people do nothing but design the equipment, and there is a really good design philosophy behind the build of the machines. And Hermann actually had this idea early on that he wanted to create a dissolver that would be capable of not only doing dissolving or dispersing, but they could also be used as some sort of a milling device. So he early on made these units compatible that they could also function as media mills, either a vertical bead mill accessory or a basket mill accessory, even a homogenizer. And we'll talk about that more later on in the presentation. But they are known as a high-end manufacturer of dissolvers, bead mills, basket mills for lab, pilot, as well as production. And about 5 years ago, we started offering production capability here in North America, and it's very successful. And people really like the flexibility and adaptability of the equipment. So it's a worldwide company. They are represented in about 65 countries all over the world. They are known innovative. About 40% of everything that VMA-Getzmann makes or builds is custom. So there's a lot of new, we call end-use markets, for example, battery or fuel cell, that require custom design. Some people like argon gas or nitrogen blankets. So with that, they can accommodate that in their design process. And a lot of the equipment that is made today is actually customer specific or application specific. So that's one of the strengths of the company, is being really flexible to these customer requirements. And the idea behind the product offering was really to create a solution not only for lab, but also make that scalable for pilot as well as production. And when you want to have scalable equipment, you need the right software, and you have to be able to come up with numbers that make sense and that are scalable. So that's one of the strengths behind VMA-Getzmann. And we also have laboratory capabilities in Germany at VMA. You can see the picture at the end. We also have a lab at our sister company at Big Additives in Wallingford. And that's also an important point we want to stress. We welcome people that have applications that then want to take a closer look at the equipment. We want to invite you up to our lab at Big Additives in Connecticut and try out your product on our disper mats and show you the results. And then also we're able to tie in some of the chemists on the additive side that help with formulation improvement and so on. So we don't want to just come across as a company that sells hardware or dispersion equipment, but also provide the entire solution, meaning also the additive support, which is very important as part of the overall package. So we're the only company that really brings that to the table. And BYK USA actually was the originator, if you want to call it that, or the party that actually started to bring the disper mats over to the US in 1988. And a lot of customers came to the lab and said, wow, these units look really interesting. We would like to acquire them also. So that's when we made the strategic decision to include the disper mat line into our BYK-Gardner product portfolio. And we now have an exclusive relationship with VMA for North America for the last 30 years. So we're the exclusive distributor. We manage everything from the sales point of view, as well as service, maintenance, and repair of the equipment, everything stateside. So with that, just again, lab pilot plant, very important for people to remember that we cover everything. So when we talk about the dispersion process, it's really important to understand what we're actually doing. And when you look at this picture, you see on the bottom these larger, we call them, let's say, building blocks. And these are particles that are fused together by these invisible van der Waals forces. They're like electromagnetic forces that are basically binding these particles, primary particles, together. And these large clusters, we call them agglomerates. And what we want to do is when we disperse, we want to just break up the binding forces that hold these aggregates together, or primary particles and aggregates, and turn them into agglomerates, these larger blocks. And the way we go about doing that is by using a dissolver. So when we go from the agglomerate level down to the aggregate level, we do not use a media mill. We actually would use a disperser, a dissolver with a Cowles blade, or an impeller blade, as some people call it, or a disc with teeth, as some also refer to it. That will give us enough shear force to really break up the binding forces and turn these agglomerates down to aggregates. And that's what we'll primarily talk about today. When we talk about taking the aggregates and turning them into the primary particle size, this is actually the second part of our dispersion process, which is the milling or fine grinding or fine dispersing, where we actually use a media mill, like a basket mill, a horizontal mill, or a vertical bead mill, or some people, familiar with three-roll mills, which we don't offer for a number of reasons. But basically, that's when you go from the aggregate level down to primary particle size. So the first step is also using the dissolver. We're not only breaking up the van der Waals forces, we're also wetting the surface of solid particles. And it really is a mechanical breakdown of these associated particles. And then what's really critical is that we always keep in mind that we somehow have to stabilize these smaller particles when they're in a suspended state so they don't reagglomerate. So for that, we also have to use different types of dispersants depending on the end use. And big additives has a big selection of those, and then they can be very helpful with giving advice on selecting the right dispersant or other types of additives that go in. A defoamer would also be one of them that might be needed. So it's really critical to remember when we talk about the dispersion process is that we are not trying to destroy particles. It's particle size reduction by merely breaking up binding forces, turning these larger blocks into smaller blocks. And the shear forces are really responsible for that separation, nothing else. And then again, the right additive will allow us then to keep these particles that have been reduced in a suspended state. So this is actually a very good slide. It kind of shows you the entire dispersion process. So pre-dispersion is what we talk about today, which is using the dissolver. What's very critical here is the correct tip speed. So some people call and say, hey, what's the RPM on the machine? How high do I have to turn it up? We always tell customers, it is not about the RPM. Yes, RPMs are important, but it's about the tip speed, which is the actual speed of your blade. And depending on the size of your disperser, the large production scale dispersers don't run at very high speeds. They can go up to about 3,000 RPMs. And when you look at a lab dissolver, we have some that go up to 20,000 RPMs. Yet when I attach the correct blade size, the tip speed should be identical. And that is important when you upscale. So for that, we want to remember that the correct tip speed window, or the optimum tip speed window, as we call it, is 18 to 25 meters per second. That's really important. And that is a window that allows us to properly pre-disperse and break up the binding forces and turn these larger agglomerates down to the aggregate level when we maintain 18 to 25 meters per second. Now, as you can see, when we mill and we fine disperse, we actually run with a lower tip speed, 10 to 16 meters per second. So that is a big difference between the two steps. And then, of course, when we use a dissolver, we accomplish the deagglomeration by using a dissolver disc. Whereas over when we disperse or mill or grind, we actually have different types of milling attachments. So a vertical bead mill, we call it APS, a basket mill, or a standalone unit, a horizontal bead mill. And we'll talk about that in part 2, the advantages of each one of those and why you would use one over the other. Okay, so another critical element when we start the process pre-dispersing is always selecting the right diameter blade, and that really depends on the volume of product. So in a nutshell, we are always aiming for about a 50% loading in our container. We can go up to about 70% and as low as 40, but 50% is kind of the optimum. If we go higher than 70, you're going to have a risk of spilling the material if you increase the tip speed. And if you're below 40%, it's more difficult to oscillate and find a really good sweet spot. So 50% is ideal. And then we want to aim for about 1/3 the diameter of our blade versus the diameter of our vessel. That's where we start. And of course, we can increase or decrease the diameter of our blade, but that is kind of like the optimum ratio. Now, if you look on the right side, you see that picture right there, that table. And basically what that tells you is that there is not one blade that fits everything for every container. So basically, let's take one quart that's 1,000 milliliters about container. And you can see that the range for blades can go as low as 30, but all the way up to 70, depending on the viscosity of my material. So if we have something that is really low in viscosity, say, let's say 500 centipoise or less, similar to like water, then I want to use a small blade. If my viscosity increases, then I will also go up in blade diameter, all the way up to 70 when I have something very thick, like a paste type material. Then I want to use a large blade to really start, allows me to move all the product around the container. If my blade was very small, like a 30 millimeter blade, and I have 50,000 centipoise, what's probably going to happen is the blade is just going to kind of spin in the middle and your product will kind of sit around it. So we want to increase that blade diameter to get really good flow of the product in our container. So that's important. And we also have that table on our website where you can find that also, or we upload the presentation as well. One more thing also, when we talk about containers, you can see the picture up there. These are jacketed vessels. When you're pre-dispersing, it usually is not as critical for that you cool your mill base, because pre-dispersing is about 15 to 30 minutes. And usually after that, you are pretty much done and you move on to the fine grinding or milling. But you want to keep in mind that you maybe want to keep on using the same container, especially if you're using a basket mill or a vertical bead mill, and then you want to be able to cool the mill base. So that's why we always recommend when you're dispersing or milling that you use jacketed vessels. They allow you to control the temperature and make sure that you are in the correct working range and that it doesn't overheat your product or lead to some other dangerous environmental conditions. So you always want to make sure that you have proper cooling capabilities, because dispersing, obviously, we're putting energy into our mill base, and if we're milling, we're going to put a lot more energy in there, and temperature will increase very rapidly. So for that, we want to make sure that we use jacketed vessels. Okay. Another very important point, as I mentioned earlier, was our tip speed. Again, 18 to 25 meters per second is optimum when I'm pre-dispersing, 10 to 16 of our rotor speed when we are milling. But we will be able to calculate the tip speed. So this formula right there is really important. And basically, it allows you to calculate the tip speed based on the information that you have, which will be your RPM and the diameter of your milling disc. So here we go. It's pi times the diameter of your milling disc times the RPM will be actually the tip speed. If now I want to calculate meters per second, then I will divide that formula by 60. But I will also express the diameter, D, in meters. So if I have, let's say, a 50 millimeter blade, I would then go and multiply that by 0.05 times the RPMs times pi, and then divide everything by 60. That will give you the value for meters per second, where you want to aim for 18 to 25. Now, some of the higher end models, we'll talk about some of the different dispermats we offer. The C technology will actually calculate that for you, so you don't have to do that yourself. But that is actually one of the most important formulas when you're dispersing, is what is actually the tip speed of my blade, and it's not just how fast, what's the RPMs. So that's only one of the values that we need to calculate the actual peripheral velocity or tip speed. Okay, then we have something else when we pre-disperse. We call that the donut effect, and it's actually literally called that. It's a visual cue. When I look inside of my container and I'm optimizing my tip speed, I'm running at a reasonably nice viscosity for dispersing. Let's say 2 to 5,000 centipoise is really a sweet spot. I'm able to put in a good amount of energy. I should be able to see the formation of a donut as I'm adjusting my tip speed to be in that optimum window, 18 to 25 meters per second. And then basically I would see that part of my blade would be exposed, and then I would actually see the formation of a donut appearing around the edges of my blade. And that gives me the visual cue, hey, I'm pre-dispersing, this looks good, let's maintain that donut and then do that for about 15 to 30 minutes. And if everything is done correctly, we should be able to reduce our particle size anywhere between 10 to 30 microns. That's where we want to kind of be before we start the milling process. We can't really be any smaller than 10. It's very difficult to get smaller with just using a cow's blade. It would take a very long time, and it's just not possible because for most products anyways, because we're not able to put in enough energy by just using a cow's blade with teeth. So if I want to go smaller than 10 microns, I really need to do the media milling or the grinding with media, allowing me to do that. Here you can see that the deagglomeration, the breakup of these binding forces is exactly at the point where my teeth are located. And there's also the agglomeration that takes place on the bottom of my blade. You can't really see it on this picture. I forgot to put it on there, but it actually is also part of the deagglomeration. It goes on below my blade. I'm also dispersing there as well. But it's really right around the edges of my blade where that happens. So if you look at this picture, that is actually a donut. As I described it earlier, you can see the blade exposed kind of in the center. You're looking at a really good optimum dissolver batch with the right tip speed, 21 meters per second, and we're putting in about 850 watts of energy. So that tells me that I optimize the tip speed, I have the right blade diameter, the blade position is correct, and I'm actually seeing a really nice looking donut. Now, it can so happen that I still run at 21 meters per second, but here is a problem. I'm only able to put in 320 watts of energy. And our Dispermats, some models will actually show you what is the amount of energy that you're putting into the mill base. Well, what's happening here? Probably is that my viscosity is very low and I have a very small blade. So therefore, I'm not able to put in a lot of energy into my mill base. So I'm also not able to see a really nice donut because the donut would collapse as soon as it's formed because of my viscosity. So I'm dealing probably with something probably below 1,000 centipoise. And it just, my blade diameter is very small and I'm able to maybe pre-disperse, but it would probably take me quite a bit longer to do the particle size reduction. And I may want to switch out, either get a larger blade diameter to put in more energy, or I may want to tweak my formulation to see how can I increase the viscosity a little bit. That will also allow me to put in more energy. And then we have another scenario where here, for example, we don't have a donut effect at all, but we're putting in a lot of energy and we're running also 21 meters per second. So here, what that means is we don't have a donut effect because my material is so viscous that it just wouldn't create a donut. But I'm able to put in a good amount of energy, so I know I'm pre-dispersing. So what you can do is maybe change the diameter of your blade, which I don't think is needed because you're putting in 900 watts of energy. Maybe what you could do is maybe reduce maybe the viscosity somewhat of your material to make the flow characteristic, the rheology a little bit better, that you would be able to see a donut. But other than that, it's also probably, if you reduce the viscosity, some of these materials can be very thixotropic. And then it happens that the material could sit around the edge of the container wall or even cling to the container wall. So by modifying the formulation, you may be able to move more of the product off the container wall, get a better homogenization or dispersion as a result of it. So that could be something to look at also maybe from a formulation standpoint. But it doesn't mean that you're not putting in enough energy or that you're not pre-dispersing just because you don't get a donut effect. So there's different ways that you can look at that, but that is an example of why you wouldn't have a donut. Okay, so this is again, very important, the dispersion duration, again, 15 to about 30 minutes. The donut effect, ideal. It's not always a must, as you just seen in some of these examples, but it's a visual cue. If you have it, you know, hey, I'm doing something right. Tip speed, again, can't stress that enough, 18 to 25 meters per second. Geometric consideration, always, okay, blade to diameter to my vessel diameter. Again, 1/3 is where we kind of start out with. And then we can go either up or down depending on the formulation and the viscosity of our batch. There's many different types of impeller disc, and even now some of these newer end-use markets, they don't allow any type of metal or steel. So we have impeller discs that are coated, with ceramic, for example, silicon carbide or zirconium oxide. So there could be a number of different ways of coating these impeller discs or cowls blades, or even designing them for very specific applications. So we can also do custom design of these impeller discs. The amount of mill base, again, 50% is ideal. Pigment filler concentration, always important to keep that in check. Temperature, again, we try to be as low as possible. Cooling, always important, especially when we move over to a media mill attachment. We want to make sure that we don't have to swap out containers, and we can do everything in the same container. So jacketed vessels have a big advantage because they allow us to properly maintain a certain temperature. And then again, the additives are critical to give us better wetting, dispersing, and no flocculation post dispersing and milling. And then once we achieve everything, we should be able to be between 10 to 30 microns of particle size. And that's when we then move over to the second part, which is the milling process, which we'll talk in a few weeks. So here, just a quick overview of some of the different technologies. So we have simple lab dissolvers. So that actually what you're looking at is the brand new CV3 Evo. We're going to release that in April. It's a beautiful lab machine. Great thing is got upscale software. It allows you to really precisely scale that up from lab to pilot to manufacturing. Maximum RPM 20,000. We are able to attach many different accessories on here, different blades, obviously, but it comes with a set of blades, but we're able to attach bead mills, basket mills, rotor stator vacuum systems. So all the things will be able to fit onto the device. And also that's true with all of our other disper mats. They are functioning also as homogenizers, emulsifiers, and of course as dispersers. But these are all different attachments that you could purchase and put onto a disper mat to work for many different applications. Here is a good picture just showing you this is actually an AE model right there, kind of our flagship disper mat for upscale and lab applications. On top left, you can see a rotor stator attachment, a vacuum system on the top right, the basket mill attachment on the bottom right. Then we have a wall scraping unit and also a vertical bead mill on the bottom left that can be attached to the same machine, and making this a very versatile piece of equipment. And that's kind of going back to that design philosophy that we spoke about earlier that Mr. Getzmann had in mind when he started this company. There's a big advantage to that is that when companies buy dispersers, they usually want to buy them for more than one project. So this allows them to cover a lot of the different applications or, end-use markets or whatever you want to call those, or products by just buying the different attachments. So we have a very simple DLC, very quick and easy, relatively inexpensive, low maintenance. All of our motors, doesn't matter what model you buy, LC or anything bigger, we use brushless step motor technology. I can't stress that enough. These motors are the best in the industry. There is no belts, there's nothing to grease, there's no maintenance on these motors. They are the most quietest motors on the market. You can hardly hear them even at high speeds, and there's hardly any vibration. So anybody that's ever used a Dispermat knows that, and they always point out how quiet these are, and they will never break. We have some Dispermats that are in use for almost 40 years now here in the US, and these Dispermats are still working correctly today on the same motor. Then we have that new CV3 Evo that's coming out in the end of March, early April. There is going to be two versions. We're going to have a standard version and an advanced. The standard is going to be exactly what you see here, but the advanced will allow you to also store the data and port it over to a computer and be able to store batches by name. But more importantly, it also allows you then to upscale very precisely from the lab to manufacturing. You can also run this model with constant power instead of just constant speed. So that's what we saw earlier when I showed you that slide with the disperser batch where we saw the different energies. So I can run, instead of a certain speed, I can run with a certain amount of energy, and then the machine will automatically adjust the speed to always maintain the energy needed to disperse a batch or upscale. So that's very important. And also when I upscale, it allows me then to calculate, hey, how much energy will I be using to disperse or mill a batch in 1 hour? Because I know exactly how much energy I will be using to do it with that constant power feature. And then the advanced model with the upscale capability also will come with a scale that sits right next to the disperser, and they'll allow you then to weigh everything, and the data or whatever you're weighing will actually be displayed on the scale itself, and then you can store that. So it's important when you want to store batches and you want to replicate that later on, that you have all that data available for good reproducibility from batch to batch. Then we have a CN line, very popular here in the US. It's a great model. What's beautiful about it, it's very simple, gives you good information on the control panel, but also very scalable. We also have models that can go up to 150 liters within the same CN line for pilot, and then it's very easy to scale that up to manufacturing. That's what the control panel looks like. So we have our speed, we have our torque value, which is an indirect measurement of viscosity. We have a timer function temperature. It'll also show us the actual blade height inside of our mill base, which is also very important. And because if it's an opaque finish, we don't really know always where's my blade. And by having that on the display, it'll show me exactly where's my blade. So that's the C technology. That's the most advanced control panel that gives you speed, energy input, a torque value. It'll give you also the tip speed on the top right. We spoke about that earlier. Temperature and timer function. All of our equipment has redundant safety features, container clamping system, the working height area adjustment. So that means that you have to set an upper and a lower threshold depending on the container size, allowing you to operate the disperser when the blade is in between these two thresholds. So that means that nobody would be in danger of having a spinning blade outside of a container at 20,000 RPM. If you were to lift it up, the blade would stop at the top reference point that you would be setting, and then the machine would just stop right there. So we wouldn't be allowed to go above that point and have a spinning blade outside of the container. And the bottom reference point will actually stop the blade from hitting the container bottom. So you have these two buttons right here. We call them H1 and H2, where you can actually digitally set those two reference points, so the top and the bottom point in your container for safe operation. And then we have also the container clamping system, ensuring that the container is always perfectly centered, it's always clamped properly, and it does not wiggle around. Only if your H1, H2 setting, the reference points are correctly set, and your containers are clamped tight, these two fields will light up green, allowing the operator to run the machine. If one of these is red, you cannot turn on the machine, it will not power on. So this is very important. It's all about safety, and we have seen people get injured or product flown around the lab. This should not happen. with the safety features of these Dispermats. Okay, and then we have the AE premium line for upscale, giving you all the features we just discussed with that net power, with that constant power. It's perfect for scale up. We can do a net power calibration, basically setting all the values to a 0 point. So the machine, when it runs without product, it would already use torque, or energy. So by doing a net power calibration, I would set all these values to a 0 point. So when I'm running my product, then the energy or the torque would only be related to my product and not the machine input. That's also important when I'm upscaling. And then again, you can store all the data and give batches a name or a product ID number, and then recall that at a later time. But really, really nice model for the lab and pilot. And then also we have that in manufacturing. Just an example here, US, we have customer that bought 3 really nice Dispermats for dispersing. These are very viscous materials, actually, some of them over 100,000 centipoise. So they actually have an integrated wall scraper system. And there is actually larger containers. This is actually the smallest production scale machine that we make. That's the SC115, but we also make them much bigger. But that's what the customer's requirements were. And then again, they can also be used as media mills also by attaching a basket mill or homogenize on them as well. Okay, so that covers it for today. We went a little bit above the 25-minute window, but I think some of the critical parts needed to be talked about.
Yep. Nope. Good stuff, Andy. Appreciate your expertise here. Couple questions in here from Christian. How can you reduce the damage of effect pigments, aluminums in dispersions?
It's difficult, I mean, obviously our sister company is Eckhart, they use Dispermats, but you have to it's a good question. And you always run into this problem when you're dealing with the effect pigments, because you don't want to destroy them. You actually want to kind of blend them. So basically, the recommendation there is you really have to dial back the amount of energy you're putting in, the speed. We have some customers that actually use a propeller blade instead of a cow's blade, so the teeth don't damage the dispersion or the aluminum effect pigment. But it's very important. If you damage the aluminum effect pigment, then it's pointless, right? And you're not going to have a good looking product. The point of dispersing is also that I have good color development, good gloss, good appearance of my material. And if I damage my effect pigment, I don't have proper alignment of my effect flake, and therefore giving me, diminished appearance, if you want to call it that, or some other side effects based on improperly dispersing. I hope that answered the question.
Yeah, good. Christian, if you'd like to elaborate, just drop it in the chat here. Okay, next question from Daisy. This is regarding the CV3 Evo. 25 meters per second is like 19,000 RPMs for a CV3 with our 20 millimeter diameter blades. This seems excessive for small laboratory paint grinds, 50 to 250 milliliters. Is our logic correct? Most people we talk to run around 1,800 to 2,500 RPMs only.
No, it's 1,800 is absolutely not enough if you're properly predispersing. I mean, we did not come up with that. That's kind of like industry norm, 18 to 25 meters per second. I've been doing this for almost 20 years, and I can tell you that the numbers align with what we see in the lab. Mm-hmm. Of course, certain pigments may disperse easier than others. 25 meters per second is the upper limit. So you may be able to reduce that, definitely go down 1,000 or 2,000 RPMs, and you should still be hitting that window. Or what you can also do is maybe change the diameter of the blade, go up 10 millimeters, use a 30 or 25, and then you'll also be able to reduce the blade diameter. But if you don't know enough, I don't know anything about your end use market really, but if it's a big pigment dispersion or ink or anything like that, I think that's correct what you're doing. Maybe a little bit on the higher end, but I don't see anything wrong with that. 1800 is definitely not enough. I would not recommend that at all, unless it's a production size unit. You have a really, really large blade, then it may be okay. Or if you're blending, people sometimes use the term dispersing and mixing interchangeably, but they're not the same. We all know when we disperse, we're actually breaking up these in Van der Waals forces. When we are mixing, we have low speed, like 1800 RPM, for example, and that is a blending operation. We are not dispersing. You cannot put enough energy into your mill base with 1800 RPM.
Okay.
At least that is our experience.
Right. And, and to test that out, the great dispersion lab in Wallingford, Connecticut, everybody's welcome to come out with material. We can do some testing. You can test it on the equipment. You can have the additives folks there. It's a great way to trial some things.
I want to stress we're going to be at the American Coating Show in April, right? I think.
Yeah.
It's May. I apologize. I know it's either April or May. I think it's
29th through the 2nd, I believe, in Indianapolis.
Of what? Of April?
Yes, end of April,
Okay.
first part of May.
Yeah. So we will have actually the new CV3 Evo at the American Coating Show. We'll have a number of other disper mats for you to take a look at, and we also have a production scale disper mat there also for the first time ever that we brought one over to the US to show at the American Coating Show. We do it at the European Coating Show every year, but this is the first time that we actually show it at the American Coating Show. So please come by the booth, and we can send you an invite to the American Coating Show as well. Just ask.
Yep. We can definitely do that. All right, some good questions here. Jack writes, can you compare a rotor stator to an open cow's blade?
Not really. I mean, a rotor stator is gonna put in. I mean, depends on the diameter of the rotor stator, right? But if it's optimized for the vessel diameter, you should be able to put in a lot more shear into with the rotor stator just because of design. It's a homogenizer. It usually works really well with low viscosity products. So if you're dealing with high viscosities, forget it. It's not going to work well because the rotor is going to just sit in the middle of your container and the product will not go through the gaps. So it's really good to use for very low viscosities, close to like water. I mean, anything around 1,000 centipoise is going to work really well. I mean, we've seen higher viscosities also work, but that's like really optimum. And then some customers, believe it or not, are using that in lieu of a milling system. We especially some of these new end-use markets, fuel cell or battery. I mean, some customers might do Boehmite particle size reduction milling that they would be actually using a rotor stator to accomplish that now instead of a bead mill. So there's huge advantages if you're happy with the particle size, is that the cleaning and the operation of a rotor stator is a lot easier than a bead mill. But I would say that comparing the two, just the cow's blade to a rotor stator is very difficult. They're different design and serve different purposes, really.
Nope. Good stuff. Good stuff. Okay. Next question here. What speed would you recommend for a coating such as epoxy or polyurethane?
I would say depending on the viscosity, but as the formula before, try to be between 18 to 25 meters per second of tip speed. So look at the diameter of your blade. If it's a 50 millimeter blade, take that, your speed, let's say 5,000 times pi 3.14 times 0.05 and divide everything by 60. And ideally, you want to be between 18 to 25 meters per second. So we have a lot of customers that are dispersing those type of materials, and the tip speeds are pretty accurate.
Nice, nice. Okay. Next question, Mohammed. Should we increase viscosity if we're not getting the donut effect? Add thickener? Do you think this will affect milling later on? What is the optimum viscosity for good milling? A couple questions.
So that's a loaded question. I mean, first of all, it doesn't always mean that you're not properly pre-dispersing just because you don't have the viscosity. It means you may need to change the blade diameter. The donut is the visual cue if you optimize everything. But as I mentioned earlier, there is a lot of times where the product doesn't allow you to have a very low viscous material. So or increase viscosity, right? Formulation is a certain way and it can't be changed. So you adjust it by the blade diameter. Really, that's the way to go about it. And then from a milling perspective, again, the optimum for us is 2,000 to 5,000 centipoise, dispersing or milling. Milling, it's important that depending on what type of mill you're using. If you're using a basket mill, obviously, it's very important that my material flows really well. I can mill even as viscosity is as high as honey, as long as it flows. But it's going to take longer because of the circulation through the milling basket and everything. So 2,000 to 5,000 is really good, but no problem. Anything higher than that. Also, when you use a horizontal bead mill, the problem becomes when it's a paste and it no longer moves. Then you really have an issue because there's no way for a paste to go through a basket mill or through a horizontal bead mill. I mean, it might be possible with a plunger setup, but it's very tricky and not recommended at all. So you should have flowability of your material. And if people ask a simple trick, I always tell them, take your container and turn it over. And what happens? Is the material running out or does it sit in the container? If it's running out, it's millable. If it doesn't, if it's stuck in the container, it doesn't want to come out, you're going to have a problem milling. You may want to reduce the viscosity.
Mm-hmm, mm-hmm. Okay, next question. In terms of choosing the right equipment, what can you tell us about nanoparticles dispersion at the lab and manufacturing process?
So that also depends on what is the actual particle size. Are we looking just sub 1 micron, or are we going down to, 900 nanometers? Are we going below 500? Are we going below 50 nanometers? So there is different types of equipment. Pre-dispersion is always the same, even if I'm dealing with nanos, slurries, because pre-dispersing, we're getting the material ready for fine dispersing. And when we're talking nanoparticles, there is a threshold for basket mills. So we are looking at 400 to 500 nanometers maximum for or minimum for a basket mill. Anything smaller than that, we use a horizontal media mill. And there we can, with the nano kit that we offer, well, we can adjust the bead size, and we're able to go down to 0.1 millimeter beads. And we're actually able to really mill the material down to sub 100 or even sub 50 nanometers. It may take a very long time, depending on the formulation and what it is, but we did it, and we have customers that are doing it on a regular basis. Nice. But we'll talk more about that in part 2 in a few weeks when we talk about this, the milling part.
Perfect. That's perfect.
Did that answer the question?
Yeah. If not, just log in the chat and we'll get to it. Elaborate if we miss something. But thank you, Andy. Next question here: lab to bulk upscaling, lab mixing time versus production mixing time. How to develop a better correlation? Is it maintaining the same energy of the lab versus the bulk?
It's only one part of the equation. We look at everything. So a great question. When we upscale, what are we looking for? First of all, tip speed should be the same. We looked at the ratio blade diameter to vessel diameter is the same. We look at the height of the blade in the container. Is it the same? We look at the filling ratio of my container. Should be the same. We look at cooling. Is the temperature the same? These are all the critical values. If I'm running with constant speed, well, tip speed is very important. That shows us everything. But we also should maybe look at the amount of energy we're putting in. Also very critical. And a lot of people, that's why they like the constant power, where we lock in a certain amount of energy in lab and then scale that up all the way to manufacturing. Very, very important. Our equipment, I have to say, scales really close to almost a ratio of 1-to-1. Not exactly, but we can expect very close correlation between the lab and the actual milling time or dispersing time on a large scale manufacturing size disperser. Then back one other critical point. Formulation needs to be also the same, same additives, raw materials, that you have the same rheology, viscosity of your material in lab versus manufacturing. If you have all these parameters the same, you should also expect to have very similar upscale results from lab to manufacturing.
Okay.
We can help you there in more detail and show you some of our capabilities if that's something you're interested in. Also the diameter not only of our blade, but also the design of our blade should also be the same.
Yep, and that's right. Like Andy said, if you would need to reach out, you can go to dispermat.com, or you can just hit reply to any of the marketing messages you get. It'll come to my team, and we'll funnel that to Andy and his team, to get back with you. So don't hesitate if you have any questions later today, next week, next month. We're here to help. Another question here: how can we calculate energy?
I can share that formula. So if I don't have that on me right now, are you talking about the energy that you're putting in, or kinetic energy?
Yes.
Maybe you want to make that. I can share that. I don't know that offhand, but there's a formula. I don't have it in this slide. But if you I have it in part of my milling presentation. So if you're joining next week or in 2 weeks when we have our part 2, there'll be a slide on how to calculate energy. Okay. So
Perfect.
that is a great question. I apologize. I don't have that right in front of me at the moment.
No worries. And Mohammed, we'll follow up with you directly with that information. So let's see. Keep the questions coming, folks. This is great. We have a few minutes left here. Let's see. What is the recommended, and this might be into the milling area, what is the recommended upper temperature limit during milling?
That's a good question, but it really depends on the material. Are you running solvent? What is it that you're trying to mill? We always say room temperature is ideal, especially, solvents like to evaporate, as you go up. But then we have some that are looking for a reactor with a reaction. They need to be 180 C. So it really depends on what your formulation is and the material that you're milling or dispersing. But we actually can accommodate all the different ranges. So for high temperature stuff, we can actually build dispersers with cooling shafts and all that other stuff. Triple wall containers we have built. So it depends. There is not one, but usually when we run it for our standard pigment dispersions, we're looking at room temperature.
Okay, good.
Maybe a little bit above 50 C, but not much higher than that.
Yeah. This might be the same question. How do you calculate the energy? What is the optimum ratio for tip speed to energy?
Yeah, we'll cover that. That's in the formula. So we'll show you that in 2 weeks.
Yeah, on the 27th.
Yep.
Yeah, keep in mind, scroll up in the chat. I put that link there. Just copy that, paste it in your browser. You can register. Additionally, you'll get an invite to that via email. So make sure you register to catch that. If you're not able to attend physically, register anyway, because after the presentation, you'll receive that recording link. So
we also have a YouTube channel. If you guys want to post that, John, people can go on there and.
Let me do that right now. Let me find that. And get that.
And if you're interested in more information about production scale Dispermats or the new CV3 Evo, reach out to John, or you can even email me. Go through our company. We'll provide you with more information on the new CV3 Evo.
Yes, I just put the YouTube channel in the chat. We put all these recorded presentations there. There's a tour of the Wallingford lab, a quick video tour, and some other things. So check it out and get back with us if you need anything. What else? Got just a couple minutes left. Any final words from you, Andy?
No, I really appreciate everybody coming online today. It's very nice to see that we still have started these presentations right around when COVID started 4 years ago. And we see that there's still a big demand for learning more about properly dispersing and milling. I think it's great to see that we have so many people attend our seminars. It really is really nice. So hopefully you use Dispermat in your lab or production. If you don't, maybe that's something that you want to look at. We'll be very pleased with the technology and the performance. I can tell you that.
Yeah, good. And hey, here's a good comment I want to pass along to you, Andy. From one of our viewers, I really appreciate the presentation. I've been in this industry for a couple of years and I've learned so much today. So your message is getting out, Andy. So thank you for sharing your expertise. That's always really good to hear because we have a pretty packed webinar schedule. If you're into dispersion specifically, we'll run about 10 or 12 webinars throughout the year. Again, the YouTube channel, we keep the archive of them there, so you can take a look at ones from last year and previously. And any new ones we'll post there. So hit subscribe so you'll be notified of those. And, if you have any questions, we're here to help. Andy, his team, a wealth of knowledge. And we're all about providing solutions, saving money, reducing waste, improving efficiencies, all that good stuff that everyone needs. So thank you for joining us. We look forward to seeing you on the next webinar. Again, on the 27th, we're running the second part to this webinar, again, with this Q&A at the end of it. So, we look forward to joining you, and thank you so much. And we'll see you on future webinars. Thank you again.
Thank you again. Appreciate the comments, and hope to see you in 2 weeks when we have our next seminar. So have a good one.